Hi everyone, Mr. Bowman here. We are going to spend some more time taking a look at the relationship between arc length, radius, and central angle measure. But what we're going to do now is we're going to look at it in terms of motion. So what we're really going to do is take a look at the relationship between linear velocity and angular velocity and the radius of the circle. So to start out with, I want to illustrate this statement at the top of these notes here that says points on the radii of concentric circles have the same angular speed but different linear speeds when they are different distances from the center. So to illustrate that point, I have an animation here, and what you're looking at is two concentric circles, meaning they have the same center, the solid black circle and the dashed line black circle. And what you're going to see is you're going to see a counterclockwise rotation of the radius. And I want you to pay attention to the 2 points, the solid red point and the pink open point, as they rotate. And what you'll notice, I hope, is that they are rotating at the same angular velocity or speed, but the outer point, the open pink one, is traveling a greater distance over that same period of time, meaning it's traveling at a greater velocity. So you see right about here, they hit pi over 2, both of them, but the outer point traveled more distance. Pi, 3 pi over 2, and finally one full rotation of 2 pi. So essentially what we see is that they take the same amount of time to rotate the same angle, but the outer point covers more distance in that same amount of time. So it's moving at a faster linear velocity. Now you might be saying, well, wait a second, they're not moving in a line. So how do you call that linear velocity? So I want to demonstrate that with this next animation. And think about a point on a circle or the circumference of a circle. And as we rotate, that circle is going to make contact with this road here, or maybe a tire on a road. And what we're going to do is we're going to unwind the circumference of that circle and show you that over one rotation, the tire or wheel, whatever it is, will travel a distance equal to the circumference of the circle. So what does that mean in terms of velocity? Well, that's where we get the phrase linear velocity. And you will see that if we change the radius of the tire, it's going to take the same amount of time to make one rotation, but as the radius gets larger, it will cover more distance. So if we cover more distance in the same amount of time, then the velocity is going to be greater. So you might be asking how that relates to the arc length formula that we've talked about before. Well, as you probably know, if you take a distance divided by a time, you get a velocity or a speed. So if you imagine that arc length formula, S equals r theta, and we take both sides of that and divide by t, what we end up with is S divided by t, when S is the distance or the length of the arc, which we just showed is going to translate into a line when we rotate, becomes the linear velocity, which we are going to call v, and r times theta over t, well, theta over t becomes the angular velocity, which we have this w for. So now we've taken the arc length formula and translated it into a linear velocity is equal to radius times angular velocity. One of the things that we talked about using the arc length formula is that theta has to be in radians, or you convert from degrees to radians. Well, the same thing is going to have to apply here. W is going to have to be in radians per unit time for us to use this. And lots of times that information is not given in radians per unit time. It's given in something like rotations per minute, for example. So we're going to have to convert with that. But before we start working with those conversions, I want to talk about some of the units associated with radius, arc length, and central angle, and some of the units associated with linear speed and angular speed, so you get kind of a feel for where we're headed with this. So the types of units that we used when describing radius are things like inches, or feet, or meters, miles, etc., things like that. Arc length, that would be the same thing, same as radius. At central angle, we might have used degrees, or we might have used radians. Now, I want to make this point about radians. If you remember, S is equal to R theta, then theta is equal to S divided by R. And if S and R are in the same units, then theta, or radians for theta, are going to be dimensionless. So keep that in mind as we go through these notes. Radians are dimensionless. Linear speed, on the other hand, would be, or velocity, if you want to call it velocity, if we added direction to it, would be basically taking the arc length units and dividing by time. So inches per hour, or feet per second, or miles per hour, things like that. Angular speed, on the other hand, would be things like degrees per second, or radians per hour, or RPM, which is equal to rotations per minute. That's a common unit. So let's take these ideas and put them into use and do some examples. The first example asks, will a point on the Earth's equator have a faster angular speed than a point near the Arctic Circle as the Earth rotates on its axis? So imagine looking down from above the Earth, down at the axis of the Earth at the center, and the outer circle is the equator, and the inner circle is the Arctic Circle. And if we put points on them and we connect them with a radius and we start our rotation here, let's say counterclockwise, you will see that their angular speed is going to be the same. Why? Because they're going to move the same number of degrees per unit time, or radians per unit time, or the same number of rotations per unit time. However, a point on the equator is going to move a further distance, so its linear velocity is going to be greater. In this next example, we're going to use our V is equal to R times W formula to solve this. So here we go. The wheels on a child's tricycle rotate at 50 revolutions per minute, or rotations per minute, or RPMs if you want to call it that. The wheels are 12 inches in diameter. Find the speed in miles per hour. The speed is referring to the linear speed. So we're trying to solve for V. So first of all, we have the radius, which is in inches. So we have 6 inches. And we want to convert that to miles per hour. So you can change the order of these conversions, but I like to keep consistent. I'm going to convert my radius of 6 inches to miles first. So what do we have? We have 1 foot per every 12 inches. Those inch units will cancel out, and then we have to convert from feet to miles. In case you don't know this, there are 5,280 feet for every 1 mile. You might want to write that down somewhere because that comes up quite often. So the feet units cancel and we're left with miles. So we've converted our radius to miles, and we'll do all those calculations in just a minute. Now we need to convert our 50 revolutions, I like to call them rotations per minute, to radians per minute, and then we're going to have to convert to radians per hour. So how do we do that? Well, we know that one rotation is the same as 2 pi radians. So our rotations are going to cancel out. And then we have radians per minute, but we want radians per hour. So we know that there are 60 minutes in 1 hour. And then our minutes are going to cancel out. And when everything is said and done, you will see that we have units of miles times radians per hour. That's an hour symbol down there. But radians are dimensionless, so you can pretty much ignore that. We just treated that as a placeholder. So our final answer will be in miles per hour. Now, I would suggest that what you do when you do these is that you multiply straight across for those numbers that are in the numerator effectively, like the 6, the 50, and the 2 pi, and the 60. And then you divide that by those numbers that are in the denominator, the 12 times 5,280. So if I were going to do this on my calculator, it would look like the following. The expression you see here would be all the terms that make up our numerator, so we're going to multiply those out first, and we get an answer that is rather large, but then we also have to divide by the terms that would make up our denominator, which if you go back and look at the notes, are 12 times 5,280. So our final answer would be 1.78, and if we go back to the notes, that's in miles per hour. So our final answer for this is that the child on their tricycle would be traveling at 1.78 miles per hour. Please keep in mind that the units have to cancel to get to the final units that you want, and the radian in there is really, I'm just treating it as a placeholder. We can get rid of it at the end. And the reason that we can do that is that radians are dimensionless. So what we're going to do now is we're going to take that same formula and those same ideas, and we're going to apply it to a few different problems. So this next problem says Olympic gold medalist Mariana Pajon raced on a BMX bike with 10-inch radius wheels. When she was traveling at 24 feet per second, how many revolutions per minute were her wheels making? So in this case, they're telling us her linear velocity, and we need to find her angular velocity in revolutions per minute. So what I do is I start out by saying, well, we know that V is equal to R times W. Linear velocity is equal to radius times angular velocity. But what we really want to know is W. So we divide both sides of that equation by R, and it cancels on the left hand or the right hand side, and we get W, or angular velocity, is V divided by R. Now this might be a little bit more complicated, but remember, you just need the units to cancel out in the end to get the correct units, and we want rotations per minute, or RPMs. So let's start out with her linear velocity, 24 feet per second. Okay, we want to get an answer in revolutions per minute. So the first thing I'm going to do in my numerator is I'm going to take care of getting rid of the units of seconds. So there are 60 seconds in every minute, and if we were to cancel the seconds units, we'd have feet per minute. So we're going to leave that the way it is right there, and we are going to go to the radius. The 10-inch radius wheels, so 10 inches, and we want revolutions per minute. Well, you'll notice in the numerator that we have units of feet. So for those to cancel, we're going to have to convert our denominator to feet. So 1 foot for every 12 inches. And so our inches units will cancel out. So what do we have to do here? We have to multiply the 24 times the 60 in the numerator, and we have to take the 10 divided by the 12 in the denominator, and then we have to simplify that. So I'm going to pause for a minute here and do that on the calculator, and we'll come back and talk about what we have at that point. In our numerator, we would have 1,440 feet per minute. In our denominator, we would have 0.83 repeating feet. And what we would end up with would be 1440 divided by 0.833, so, or 0.83 repeating. So if we figure that out on the calculator, we get about 1,728, and the feet would cancel out, and you can verify that, and it would be 1 over minutes. Now, here's where I like to think about the radian as a placeholder. So what we're basically saying, we're rotating at that many radians per minute, but we don't want to leave it in radians per minute. We want it to be rotations per minute. So we're going to take that number, 1,728 radians per minute, and we're going to multiply it by the conversion factor, which is 1 rotation for every 2 pi radians. And you will see the radians units cancel out. So we're basically going to take our 1,728 and divide it by 2 pi. And when you divide that by 2 pi, you get an answer of 275 rotations per minute. 275 rotations per minute, or the same as 275 RPMs. In this next problem, we're going to connect two pulleys, or basically like wheels, with different radii with a belt, and we're going to look at the relationship between their angular speeds and their linear speeds. So to illustrate this with a picture, here's what we have. We have the smaller pulley, we'll call that R1, and that has a radius of 4, and the bigger pulley, we'll call that R2, is 8, and they are connected by a belt. So as one pulley rotates, the other one rotates as well. Well, it turns out that as this belt is moving, it has a linear velocity. But that linear velocity is the same for those two pulleys because they're connected by the belt. So, in other words, V is equal to R1 times W1, but V is also equal to R2 times W2. Okay, so now to answer the questions. What is the angular speed of the larger pulley in radians per second? All right, well, we know that it's turning at 120 RPMs. That is the angular speed, 120 rotations per minute, but it's not in the units that we want. So we're going to convert to that, and we're going to use our 2 pi radians per rotation. So basically, we're taking 120 rotations and multiplying it by 2 pi, because each rotation is 2 pi radians, and we get 240 pi radians per minute. Well, we still need to convert that into radians per second, so we have to take 240 pi radians per minute and multiply it by that conversion factor, which is 1 minute for every 60 seconds. So we're going to divide that result by 60, and 240 divided by 60 is 4. So we have 4 pi radians per second. Now, if you'd like to, you can multiply 4 times pi and you're going to get approximately 12.57 radians per second as well. What is the angular speed of the smaller pulley in radians per second and RPMs? Okay, so here's where we use this relationship that the two linear velocities are the same because they are connected by the same belt. So what we can basically say is that R1 W1 is equal to R2 W2, and we want to find W1. So we could do a little algebra here and divide both sides by R1, and the R1s cancel out here, and we know that W1 is equal to R2 over R1 times W2. Well, that's a helpful relationship there, because what we're seeing is that all we have to do is take the ratio of the two radii and multiply it by the angular velocity of the larger pulley, and we've got our answer. So let's do that. So R2 is 8 centimeters. R1 is 4 centimeters. The centimeters will cancel out, and if we multiply by our 4 pi radians per second, what we see is that we get 8 pi radians per second, which you might notice is twice the angular velocity of the bigger pulley. So what we're saying is that when you use a larger pulley to drive a smaller pulley, the angular velocity of the pulleys is going to be related by the ratio of the radii. And if we now want to convert that to RPMs, or rotations per minute, 8 pi radians per second times 60 seconds per 1 minute times 1 rotation for every 2 pi radians, and you'll notice that all the units cancel out except for rotations in minutes, and you can verify this, but this will be 240 RPMs, or rotations per minute, which you can see is twice the angular velocity of the larger pulley. And how are the angular speeds of the two pulleys related? They're related by the ratio of their radii, or the velocity of the smaller pulley is twice the velocity. The angular speed of the smaller pulley is twice the angular speed of the larger pulley. So now what we want to do is we want to take a minute and demonstrate that, how that relates to gears on bicycles. So our last demonstration here are bicycle gears, and there we go. So what you see is what is called a sprocket up at the front being turned by pedals on the left hand side, and a sprocket at the back, which is the smaller circle on the wheel, and then the wheel itself. And in this case, I have the two sprockets set to have the same radii, and they are set at 1, and the radius of the wheel is 3 times the radius of the two sprockets. So the angular velocities of all three circular parts, the front sprocket, the back wheel, are the same, but what you see is that the linear velocity of the wheel is different than the linear velocity of the chain. So over on the right hand side, front sprocket is turning at 60 degrees per second, the back sprocket also turning at 60 degrees per second. The chain speed is a linear velocity of approximately 1 inch per second, and the wheel speed, or the ground speed linear velocity of the wheel itself, is 3 times that, because the radius of the wheel is 3 times the radius of the sprockets. we are going to take that relationship between the two sprockets and the wheel and apply that to the following problem. In this situation, the front sprocket has a radius of 6 inches. The rear sprocket has a radius of 3 inches, and the rear wheel has a radius of 12 inches. And we are told that Arthur is moving the pedals of his bicycle at a rate of 42 rotations per minute. What is the linear speed of the bike chain in inches per minute? So again, S is equal to R theta, or V is equal to RW. So we're going to use that V is equal to RW formula. And V is equal to 6 inches times 42 rotations per minute times 2 pi radians per rotation, and the rotations cancel out, and what the radius, remember, those are, or the radians, remember, are dimensionless. So what we end up with here is about 1,583.6 inches per minute is the chain speed. So now that's connected to the rear sprocket. So in the rear sprocket, we're going to use that same formula. V is equal to R times W, but we're going to solve for W by dividing both sides by R. So W is equal to V over R, but we know that V is 1,583.6 inches per minute. And we want to divide that by the radius of the rear sprocket, which is 3 inches, which gives us an answer of approximately 527.8. Notice that the inches cancel out, so we'd have 1 over minutes, but we can throw radians in there because radians are dimensionless, radians per minute. But we can now convert that to rotations per minute. So we take our 527.8 radians per minute, and we multiply that by 1 rotation for every 2 pi radians, and we get an answer of 84 rotations per minute, which you will see is twice that of the front sprocket, and that's because the radius of the back sprocket is half that of the front sprocket. So we just have 2 more problems we want to solve here, and the following is if the rear wheel of the bike is connected directly to the rear sprocket, which is usually the way that is set up, and it has a radius of 12 inches, how fast is the bike traveling in miles per hour? So again, V is equal to R times W, and what we have is we have 12-inch radius, and we're going to convert to miles per hour, so we have to do 1 foot for every 12 inches, and then we have to convert the feet to miles, so 1 mile for every 5,280 feet, and then we have to multiply by the angular velocity in radians per hour. So what do we have? We have 84 rotations per minute. We're going to multiply that by 60 minutes in every hour, 1 hour. And we're also going to rotate that, or multiply that by 2 pi radians per rotation. And if you do all of that, you will get an answer of 6 miles per hour. How would this answer change if the radius of the rear wheel of the bike was increased to 18 inches? Well, the only thing that would change in our above calculation would be this 12 inches, and it would go to 18 inches, which is 1.5 times 12. So our answer would change to 9 miles per hour. And that's it for the relationship between linear velocity and angular velocity and radius.